Let's go over the first slide. Okay, so in statistics, in the SAT, they will basically test you about a number of statistics measures that are known as the mean, the median, etc. So we'll revise each of these concepts, very simple concepts indeed, but usually apply to a set of numbers. For example, imagine that we have this set of numbers, okay? When we talk about a set of numbers here, we're referring to a group of numbers or numerical values, for example, this, in which you may have several numerical values that are different, or some of them repeat, or perhaps are all the same, okay? Anything is possible with numerical sets of values that are used in statistics questions. So what is the first concept? The arithmetic mean is the same as the average, all right? How do we get the average of a number or a set of numbers? Well, we need to calculate the sum of all the elements and then divide by the number of them, that is their quantity, right? So how many can you count here? We actually count 6. So we add the values of those. Notice that even though the element 2 is repeated 3 times, I consider each with individual value of 2. So I need to consider 3 2's in the sum. Okay, so adding this and dividing this, okay, this sum actually equals 24. And then divide by the number of elements. Totally here there are 6 numbers. So we obtain the arithmetic mean. Okay, this is the first statistic measure that they will mention in questions in the SAT math part. The next concept is the median. This is another, indicator in statistics that will give you what is the numerical value that falls in a central position in a set, but when the set has been arranged from least to greatest. So, for example, if we have just these 5 elements forming a numerical set, well, something easy to notice is that you can actually see the elements arranged in an ascending manner, that is to say from least to greatest, and the median corresponds to the value of the element that falls in the central position. You know, there are 5 elements here, so the central position must always be the third, okay? And this is a little trick. For example, if you happen, to see that there are totally n different elements in a numerical set, and if there is an odd number of elements, then if there is an odd number of elements in the set, for example, 5, there is always a central element, a unique central element. And that unique central element is the third. How do we determine the position of the central element? Well, oh, hello, Madeleine. In this case, the first one, when the value of the number of elements in the set is an odd number, for example, 5, there are 5 elements here, you simply do this, okay? N plus 1 over 2. And that is the position of the median. That is, the element with this position is the median. So 5 plus 1, 6, divided by 2, 3. So the third element is the median, okay? But Of course, not in all cases, you can say that the number of elements in a numerical set of values is odd. What if the number is even? For example, 6, 10, 20, 100, etc. How do we get the median in that case? Well, consider this example. You have here a set of 6 numerical values. Okay, and we have already arranged the values from least to greatest. So there is no actual central element. Instead of one central element, there are 2 of them, these 2. Well, it's easy to spot the central elements because there is just 6 of them elements, right? So you see the 2 central ones must be the ones that have 2 elements to the left and 2 elements to the right. That is to say, the third and the fourth. Now that we have determined what are the 2 central elements instead of just 1, we need to take the average of these 2 central elements as indicated here. So if you average 2 and 5, you get the sum divided by 2, or 3.5. And this would be the median of this set. So the median can be calculated in either of these 2 ways. When the number of elements is odd, case number 1, the median is the element in the n plus 1 over 2 position. Okay? But if the number of elements in the set is even, not odd, so there are 2 central elements. How do we determine the first of these 2 central elements? Well, easy. Simply, you need to determine the average of these 2, of the n over 2 and the n over 2 element in order, and n over 2 plus 1 would be the next element. For example, n equals 6. So n over 2, 3. N over 2 plus 1, 4. So the third and the fourth elements need to be averaged in order to determine the median of the set. Okay, let's do a little exercise. Imagine that they tell me that a set of values is huge and it has 1,526 elements. All right. Which elements, imagine that this set is already arranged from least to greatest. That is, the first element is the least and the 1,526th element is the greatest one. So which 2 elements would we have to average in order to obtain the median of this set? Think about this for a moment. Which order the elements in the center of this set would have? Any ideas? What did we do in order to determine the first of the central elements in a set of 6? We simply divided 6 by 2, so that yields 3. So here the same. If we divide 1,526 over 2, what we get is what? Okay, take a look. It would be this, right? 763 or third element and the 764th. These 2 elements need to be averaged. That is, you add them and then divide the sum by 2. And that's the median of that set. Okay, so another example. If they tell me that we have set of values that has totally 71 elements. the element in which order would be the median, assuming that all the elements are arranged already from least to greatest. So which one would be the median? The number 35th, perhaps, or no? Notice the formula above, considering that this is an odd number of elements. So what do? We simply apply this. Okay, 71 plus 1 over 2. What is that? Well, actually, the 36th element is the median of the set. That is, the value of this element is the median of the set. Okay, any doubts about the median? Any questions? You need to be clear about this, otherwise, in the corresponding questions, you cannot find the median. What about this concept? Is it clear? Okay, remember that I'll take administrative silence or or a check, right? Such as you guys just did. Okay, think about it. The mean and the median actually are center related statistical measures because they actually refer to the elements that are in somehow a central position. For example, the mean is actually the average of all values. The median is the number that has the same number of elements, you know, less than and also greater than. There is a same number of elements to the right and to the left of the median in an ordered set of values. Now, what is the mode? The mode is the third one. Take a look at this. The mode is the number that appears more frequently in a set of values. In the example, that is to say this, you can see that there are 6 elements, and element whose value is 2 is repeated 3 times, while 5, 6, and 7, they appear just once each. So because 2, the number of times that an element appears within a set of values is called the frequency, right? So the one with the highest frequency, that is the mode. So in this case, 2. 2 is the mode. And what about the range? Okay, now, although these are statistical measures of, centralization, because actually they give us more information about the most common values or the average values of the elements in a set. There are also other statistical measures that try to actually record what is the distance between the elements within a set. How far away or how spread out the elements in a numerical set of values are, okay, in relation to one another. One of such measures is the range, okay? What does the range give us? Is the difference between the biggest number in the list and the smallest number in the list. But if we have already arranged the elements from least to greatest, then the range is simply, the last take away the first, okay? So it's the last minus the first. If it is an arranged or ordered set of values, or actually the greatest take away the smallest. That's a definition of the range. In the set, okay, here we can see that the least value is 2, the greatest is 7. This difference is the range of the set. Okay. These are basic concepts that we need to manage to solve SAT questions about statistics. So let's see now some examples. This question shows a chart, it's called a histogram, right? That summarizes the daily number of hours spent playing sports for 80 students at a school. So this is interesting because here we can see on the horizontal axis, it's the quantity of hours. What hours? Hours spent playing sports for different students. And the vertical axis shows the number of students engaging in sports, you know, for different ranges or quantities of hours. So, for example, we know that how many students in this histogram actually spent 0 hours or no time at all, right? Playing sports. Okay, we need to check this column that corresponds to those students that spend 0 hours. And we see that this corresponds to, okay, an estimate of 5 students. Okay, how about the students who spend 1 hour playing sports every day? Okay, this corresponds to the second column. And of course, the height of this column represents the number of students engaging daily in sports for 1 hour. So it corresponds to this part, which according to the distribution of the marks on the vertical axis should correspond to how many people approximately? Any idea? Take a look. If this is 20, this is 30, so this is supposed to be 35, right? Like halfway between the two. So each of the rows represents 5. Yes, actually, it would be, okay, 15? Really? Okay, think, between 10 and 20, how many? 10, right? 10 students. So halfway would be 5 or 15. And so one of such would be 40 and 41. Yeah, approximately. Okay, yes. So we could say, okay, 40? No. Take a look. Look, the scale vertically from here to here, there are 10. From here to here, like this is 10, this is 10, this is 10 students. So just one row, that is to say this one here, is 5. So here we have one more row. This must be 35 approximately. Okay, 35. Okay, so the idea is that we're talking about different information we can get from this. But there are totally 80 students at this school. Question 1 says, what is the mean daily number of hours spent playing sports for the 80 students? How would we calculate this? Okay, first of all, the mean is obtained by adding all the hours, the numbers of hours spent by all the 80 students, okay, by each of them, adding all of those hours, and then dividing by the total number of students. So how can we calculate actually the sum of the daily number of hours spent by all the 80 students? Well, here you can guess. For example, we know that there are 0 or 5 students, right, that spend 0 hours. So the total sum of the hours spent by these 5 students is 5 times 0. Okay, there are 35 students, that spend 1 hour. So totally, if we add all those hours, you know, it's like multiplying 35 times 1. Now, there are people who spend 2 hours daily. How many of them? According to this mark, it would be 15. So plus 15 times 2. These are all the hours spent by students who spend daily 2 hours playing sports. And finally, there is another group of people that actually spend 3 hours every day. How many of them? Okay, the size of this column corresponds to approximately, 25 here, right? So it should be 25 times, that is 25 students spending 3 hours daily. Notice something interesting. In this sum, the number of this and this and this and this should add up to 80. 5 plus 35 plus 15 plus 25 is totally 80 students. By multiplying the number of students, in each group, that is the groups for people spending 0, 1, 2, and 3 hours respectively every day, we can obtain the total sum of the hours spent by each of the 80 students, and then divide this by 80. How much is that? Okay, we can calculate that even without a calculator, right? We know that 5 times 0 cancels. So we have this one, it's 35. Here, this is 30. And this one here is 75. So we got this. 35 plus 30, okay, this one is 105 plus 35, 140. And over 80, we have 14 over 8, which is the same as 7 over 4. Or you can say that is 1 3/4 of an hour. That's the mean, the value of the mean, the quantity of hours spent by the 80 students in average. Okay, so that is part 1. The application of the definition of the arithmetic mean of the elements in a set. Now, what about the second question? It says, what is the median daily number of hours spent playing sports for the 80 students? If we were able to somehow put all the hours in a row, let's make a huge, okay, huge list of all the hours spent by every student, every of the 80 students, starting with those we want to place these hours, from least to greatest, since the values for the number of hours for any of the 80 students will be just 0, 1, 2, or 3. So we begin. How many zeros go in this set of elements? Actually 5, something like this, 0, 0, 0, 0, and 0. And then how many ones? There should be 35 ones. 1, 1, 1, and so on and on until the last one, totally 35 times. Then it comes the students who spend 2 hours every day. How many of these twos? 2, 2, 2, and so on and on until the last 2. In total, 15 students spending 2 hours every day. And finally, those that spend 3 hours every day. So it's a series of 3s up to the last one. And there are totally 25 of them. So think about this set. It totally has 80 entries or 80 elements. Okay, if you add 5 plus 35 plus 15 and plus 25, as we just said, totally 80 recordings or 80 records of the hours spent by each of these students. If we have a set of elements that is already arranged from least to greatest, then we can determine the median value by simply determining the position of the central element. In a set of 80 students, what 2 positions are the central ones? Can you tell? Which 2 positions would be actually 40 and 41, right? The 40th and 41st. These 2 would be the 2 values or the 2 elements that we need to average, because there is not just a single central element, but 2. We need to average these 2 in order to obtain the median daily number of hours. Now, here's the tricky thing. What is the value of the 40th element in this set? Can you tell? What would be the element number 40? Which value would it have? For example, looking at this diagram I just made here, enumerating all the elements in this set, you could say clearly from this enumeration here, this list, that the first element in this set is 0. And so is the second, the third, the fourth, and the fifth. But what is the 6th element? The element in the position 6. Obviously, it has to be this one. This is the number 6 position. It's 1. And the next one, that is the 7th, is also 1, and so on and on. So think about it. Which one would be the value of the 40th element? Since you know there are 5 elements here and 35 elements following in an orderly way, 5 plus 35 yields exactly 40. So that means that the 40th term must be this one. The last in the series of ones within the set, this is the 40th element. And what is the 41st? Well, the 41st is just the next to him. That is to say, 2. This one would be the 41st element. Because, you know, there are first 40 elements and then other 40 elements that make a total of 80 elements arranged from least to greatest, right? So we can see here that what we have to average, or the median of this set, would be 1 plus 2 over 2. In other words, 1.5 would be the median of the set. Okay, any questions, any doubts? Notice we are applying the same concept that we mentioned here to determine which 2 elements we need to average in order to obtain a median. When the number of elements is even, you just calculate n over 2, that is the position of the first element, and n over 2 plus 1, the position of the second element, and those values need to be averaged. It's what we did just here, okay? We have identified first that the positions to average are the 40th and the 41st. And then identify in this scheme what is the actual value of the 40th element and the value of the 41st element as well. It just happened by coincidence that they are 2 different values. So that's why we get this result. Okay, so those are the questions you will be facing in the SAT related to mean and median. Let's see more examples. Okay, now here, I want you to consider for a moment this question, okay? Then for a couple of minutes, then we'll see how to deal with this question, okay? Okay, so let's see how to solve this question, right? It says the dot plot above summarizes the number of flights taken in a year by 19 college students. If the student who took 6 flights in a year is removed from the data, which of the following correctly describes the changes to the statistical measures of the data? Well, you know always that if there is an extreme value, you know, for example, in this case, is an extreme value that is higher than the mean, right? This actual value, although it's just 1, makes the mean to be, you know, a little closer to, it's actually the mean is like over here probably, right? It must be somewhere between around this, the mean value, because of, you know, the concentration of elements or students who have just taken 1 flight in a year. So 6 just makes this mean to deviate a little to the right, to increase the value of the mean. If you remove this value, then obviously the mean will decrease a little, but will decrease. It cannot increase. So this is true. The mean will decrease. What about the median? Well, we need to be careful here. The median actually is calculated by doing what? Since we have in this element, there are 19, in this set, there are 19 elements. There are like totally 5 zeros. Then there are 7 ones. Totally 7 element ones. Then there are 4 twos. Then 2 threes. And finally, 1 6. Totally, you can see 19 elements. Okay? So, what's the median in a set of 19? In a set of 19, the median is the 10th element. Remember, we have 19 elements. So, to find the median, we just need to determine the 19 plus 1 over 2 element in position. In other words, 20 over 2, the 10th element would be the median. So what is the 10th element? Think about this. There are 5 elements here and 7 here. So totally there are 12. The 12th element is this one. So the previous one, which is also 1, is the 11th, and the previous to the 11th is the 10th. So what is the value of the 10th element? Is simply 1. It's one of the ones in this set of 7 here. Because, you know, the first 5 and the second 7th form the first 12 elements. So the 10th element is a 1. So that would be the median. Now, what happens if we remove this element here? So now the set of values would be 18 elements. Okay? We remove the 19th element, so we have 18 elements, and so we would have to average, to determine the median, average the 9th and the 10th elements. But what are the 9th and the 10th elements? They are 1 and 1. So if you average 1 and 1 over 2, that is just 1. So the median remains the same, just in this case. So this one is not true. The median doesn't decrease, remains the same. What about the range? What is the definition of range? Well, definition of range is the difference between the greatest element in the set and the least. So what is the range here? Is the difference between this, okay, think about it. The original range is the difference, okay, is the difference between 6 and 0. So this would be 6. But the later range, that is the range when we have removed the biggest element, the 6 at the end, then the greatest element would be now a 3. So it would be 3 minus 0, 3. Obviously, the range decreases. So this is also right. Correct answer is C. Okay? Yeah, several of you got it. Very good. So let's see another example question. Let's take a look at this one. It says the average weight of a group of pandas is 200 pounds. Another panda weighing 230 pounds joins the group, raising the average weight of the entire group to 205 pounds. How many pandas were in the original group? Okay, an interesting question. All you need is the definition of the average or the arithmetic mean of a set of values. Okay? You can try first, couple of minutes. All right, so how do we do this? Well, first of all, the definition of the average is what we need to keep in mind. The average is defined as the sum divided by the number of elements, right? So we have this to be 200. Okay, so according to the statement, it says that another panda weighing 230 pounds joins the group. Okay. Here, it mentions that there is another panda. So this extra panda, we don't know how many pandas exist. That's what we want to find, that is n. But we know that this extra panda would be the n plus 1th panda, okay? And this is added to this group. So take a look at this. The sum of the original group of pandas could be understood as the product of the arithmetic mean or average multiplied by the number of pandas that there was originally. Okay, 200 times n. So you can think about this. If we add an extra panda, what will be the new sum of all the pandas, that is of the n plus 1 pandas? It would be, okay, S plus the weight of the last panda, the one just joining the group. So 230. This is the total sum of the n plus 1 pandas. And this, of course, according to the definition, has to be equal to the average of the group, the average weight, multiplied by the number of elements. They give you this new average. They say that the average weight was raised to 205 pounds. So you have this. This is the average. And the average multiplied by the number of elements, which now would be n plus 1. There is one more panda. So we have another equality. Okay, interestingly, we can substitute this expression, the original sum, we can substitute for 200 times n. So this yields the value of n, right? Here we have 200n plus 230 equals, we open this parenthesis, 205 times n plus 205. And so, simplifying the expression, you have 205 times n minus 200n, that is 5n. And this would equal the difference of this and this, 230 minus 205. In other words, 25. So what do we have? N equals 5. That is the original number of pandas. Okay? Any doubts, any questions? Everything clear? Shall I repeat? You got it, right? Yes. So normally when they give you these questions about, averages, remember that the best way to use data about the average or the arithmetic mean of a set of elements is always to use the sum, because the sum is defined, the mean is defined as the sum over the number of elements. So when they give you the mean, immediately you know what the sum must be. It must be the mean multiplied by the number of elements in the set. So in this way, we formulated what is the sum for the initial set of elements, that is of pandas, and then the extended sum with the arrival of the extra panda. Okay, so that's how we can formulate this type of question. Let's see another example now. Take a look. Okay, this is interesting. It deals with another, statistical measure of dispersion that together with the range gives us an idea about the, how to say, the distance or the spreading of the elements regarding the arithmetic mean. When we talked about the range, we just, we can see how far the end or extreme values of the set are, but that really doesn't tell us anything about the intermediate values, the values in between. How spread out they are, we don't know. We only know where the least is, the greatest is, how far they are. But for all the elements in between, we have absolutely no idea. Okay, there is a statistical measure that is called the standard deviation. The standard deviation, you can understand the standard deviation in a very simple way. It is true that it has a complicated formula, but it doesn't matter because in the SAT, they will never ask you to calculate the standard deviation. But still, you need to handle the concept. How can we see the standard deviation? Okay, please interpret this term deviation the same as difference, and a standard same as average. So what is a standard deviation? Is an average difference that exists between each element in the set and the arithmetic mean of that set. Conceptually, you could think of something like this. Imagine that over here, okay, you have a set in which this is the mean value, the arithmetic mean. Okay, let's draw different, this dotted line represents the value of the mean, and the horizontal positions of these dots represent the values of different elements. So how do I calculate the standard deviation? Imagine that we have determined the arithmetic mean first, and then we start measuring what is the distance between each of the elements and the arithmetic mean. Just measure positive distances. And then, these line segments represent the distances between each element and the arithmetic mean of the set. Then average those segments, calculate the average length of the segments. That would be like average difference between the elements and the arithmetic mean. That would be the standard deviation conceptually. If you want, you can say that the standard deviation is more or less this. You can add all the differences between the arithmetic mean and each of the elements of a set. Every xi means a different value, a different element in a set of values. Take the positive difference of this, each element and the mean, add all those differences for all the n elements in a set, and then after you added all the differences between the elements and the mean value, then divide that sum by n. That is approximately the standard deviation, although the real formula is more elaborated. As I said, this is just a concept. So what does it mean? That the higher the standard deviation is, that means the more spread out that the values of a set are regarding to one another. But the lower the standard deviation is, that means that the elements or the numerical values of a set are all cramped, around the mean value. They are closer to one another, okay? Higher deviation, higher dispersion. Lower deviation means lower dispersion, okay? That they are more cramped or more together, all the elements in regarding to one another. So, think about this. The question says the bar charts above summarize the number of cars that residents from two neighborhoods, A and B, own. Which of the following correctly compares the standard deviation of the number of cars owned by residents in each of the neighborhoods? So you have neighborhood A, neighborhood B. Which one would have, the greater standard deviation? So think about it. Where is, the mean of the first set approximately, where would it be? It must be clearly somewhere around this position, right? Because most of the elements are concentrated here. This is the mean. So, and they are all concentrated, so the difference between the value of these elements and the arithmetic mean is not that much. Take a look. We can say that if this is the mean, for example, approximately, I'm not saying that is, you could say that the largest difference would be this here, but the differences for these elements is actually less because there are fewer elements that have those differences. So in average, the difference between the elements and the arithmetic mean is not that much. You could say probably that the size of this difference is something like this, perhaps, in average. But what about the other set of values? The other set of values have more values on the ends, both to the left and to the right. They are very dispersed. You know, there are high values, here, or there are many values here in this position, and here there are also values. So they are more dispersed. Clearly, the standard deviation in, the second set must be greater, okay? While in the neighborhood A, the values, that is the number of cars owned by different residents, are more cramped or closer. As an exercise, I would challenge you to prove that what I'm saying, that is to say the standard deviation of the number of cars owned by residents in neighborhood B is larger. Okay? Correct answer is B. You can try to demonstrate this by using this approximate formula. For example, for neighborhood A, how would you calculate an approximate standard deviation? Okay, you can see this. What is the sum of all the differences? You would have to say, okay, first of all, what is the total or the arithmetic mean of all these values? You can calculate by multiplying 0, right? First the mean. Calculate 0 times 35, this value, plus 1 times 30, multiplying the frequencies by the values of the elements. The values are these. This is a set of elements with only values 0, 1, 2, 3, 4, 5, and 6. So we need to, in order to calculate the arithmetic mean of this, take like a weighted average of these 7 values, right? So 0 times the frequency, 1 times the frequency, 2 times the frequency, that is 35, then 3 times the frequency, which would be 25, 4 times the frequency, which would be approximately 15, then 5 times the frequency, which would be just 10, and 6 times the frequency, which would be just 5. So this should yield, divided by the total number of people. What is the total number of people? Okay, this plus this plus this plus this plus this plus this and this. In other words, 35 plus 30 plus 35 plus 25 plus 15 plus 10 plus 5. If you do this calculation with a calculator, very easy, you get the exact arithmetic mean. Then start calculating, what is the difference between this mean and, for example, 0. 0 minus the mean, okay, just take the positive difference, annotate it. You will have to get, okay, totally, there are a lot of elements here. This would take forever, probably, but if you do the calculation, first the mean, then calculate the difference between the mean and each element, you can see that this element is like a huge list of, zeros, then ones, then twos, then threes, and so on and on, fourth, fives, and sixes. Okay, the set is like that. How many zeros? 35. How many ones? 30. How many twos? 35, and so on. That's a total set of values. If you did this calculation, you would verify that actually, once you obtain each of the values and then calculate the difference. For example, let's imagine that the mean here is what? Let's just do this out of, curiosity so that we can set like pattern, how to use this approximate formula for operating. For example, here, if we multiply 0 times actually 35, you don't need to do anything, that's simply 0, right? You have 30 plus 70 plus 75 plus 60, 4 times 5, 15, plus 50 plus 30. So this sum here is actually 315. And what is the total number of elements? Is the sum in the denominator, which is 35 plus 30 plus 35 plus 25 plus 15 plus 15. Okay, it's faster too. These two are, 70. Then you have 100. Then you have 140 and 155. So figure that this number would be the arithmetic mean. Divide this by 155. The arithmetic mean of this set neighborhood A would be 2.03. That is the average number of cars that residents have in neighborhood A. How do we calculate the approximate standard deviation for this neighborhood A? Okay, you have to say, okay, what is 0 take away 2.03? Okay, 2.03 is a positive difference. So multiply that difference by how many zeros there were? 35, right? So you need to calculate this sum by doing the following. 2.03 times 35, because it's 0 minus this number 35 times. Then the next elements are just ones. So 1 take away 2.03, the positive difference is just 1.03 multiply by 30. Then the next group of elements, 2, take away 2.03, the positive difference is simply 0.03, multiply that by 35. Then here, the next group or the next set would be 3, take away this, you get 0.97, and this multiply by 25. Then 4, take away this is 1.97, multiply by 15, plus 5, take away this, 2.97, multiply by 10, and finally 6 minus 2.03 is 3.97 times 5, the last of this. So you add all of this, then divide this by the number 155, and you obtain the standard deviation. If you follow the same procedure for neighborhood B, you will see that the value that you obtain has to be higher for the second set of elements. Okay? Obviously here, you have used your intuition only to say that in neighborhood B, the deviation must be greater because the values for the number of residents are more spread out, okay? But of course, you can calculate it. And the calculation corresponds to the very close value to the actual value of the standard deviation. Okay. If you ever study statistics or engineering or any other, for example, economics or some other majors, you will actually be taught the formula for the real standard deviation. Okay, but the concept is the most important in these questions. Let's take a look at another example here. A pet food store chose 1,000 customers at random and asked each customer how many pets he or she has. The results are shown in the table below. The number of pets, 1, 2, 3, 4 or more, and the number of customers that possess this number of pets. There are a total of 18,000 customers in the store's database. Based on the survey data, what's the expected total number of customers who own 2 pets? So think about this. This is similar to the question we saw about probabilities, okay? If you have a sample, okay, here, this survey data gives us the concept of a sample of a population. When we cannot actually perform estimations on the values of, indicators in a population that is too large to be measured, you can just take a sample and, measure over the sample that has been chosen randomly. And then whatever estimations you want to make on the real population, you would do first using the samples data. And so you do an extrapolation, kind of saying that what would be the probability, right, that in a population of 18,000 customers, you would find a total number of customers who own 2 pets, sort of. So for example, here, what is the size of our sample? It's 1,000 customers. So it's actually 18 times smaller than the real population. So out of 1,000 customers that were sampled, the number of people who possess 2 pets is 200. So what does this give us as an estimation? That 200 out of 1,000 is 1/5. 1/5 of the surveyed customers say that they have 2 pets each. So what can we expect for the 18,000 customers? You simply multiply 1/5 times 18,000. Okay, since this is the same as 2/10, so here you can, and this multiply by this, and you get 3,600, which would be the answer to this question, right? So that's another type of question in which you're supposed to estimate results for example, some preferences of a population, but based on the size of a sample, okay? So quite similar to what you did in probabilities questions. Let's see another example of this. Okay, here is another type of question in which you are given a set of values and they, plot 2 variables, like an independent variable and perhaps a dependent variable. And we want to show some association of the values of the 2 variables and using a line of best fit, which is sort of say that the association in values between the 2 variables follows a linear pattern, right? So, and this line of best fit is the approximate, line pattern that this data follow. Actually, of course, there are some values that are very closely grouped around the line of best fit or the positions indicated by the line of best fit, but there are some unusual values that may be very far from the line, okay? So here the 2 variables are the heart rate and the oxygen uptake in liters per minute. And for a person at 6 different points of his daily routine. Question is, based on the line of best fit, what is Kyle's predicted oxygen uptake at a heart rate of 110 beats per minute? So we have taken the samples of the oxygen uptake for many moments, but not exactly for 110. 110, there is no actual data here. But if we want to extrapolate or predict what would be the oxygen uptake of Kyle, it would correspond to this, right? So it means that the predicted oxygen uptake should be about 1.5 liters per minute. And this would be the answer to the question. Okay, so another typical statistics questions in the SAT. Let's see the second part for this question. Okay, you can try this one. This is another question based on the same information. Very good. We have an answer here. Look, here it says, what's the oxygen uptake in liters per minute of the measurement represented by the data point that is farthest from the line of best fit? While most of the values seem, close to the line of best fit, which shows the linear pattern tendency for this set of data, there is one that is like far, right? Okay, this is also a little far, but not as far as this one. So this doesn't really adjust to the line of best fit. So this corresponds to a heartbeat, which is approximately, you know what? Approximately, if this is 110 and this is 120, so you see here that each division must represent about two heartbeats, right? So this is approximately, perhaps, 118 heartbeats or beats per minute. And to this, what oxygen uptake corresponds? Well, this one, right? Exactly 2.5 liters per minute. The answer to the question. Okay, let's see another sample question. Okay, we still stick to the same chart, the oxygen uptake versus heart rate. Now we have a different question. Which of the following is the best interpretation of the slope of the line of best fit in the context of this problem? Okay. What you need to know in order to respond to this question is just remember the lesson about linear patterns, right? Linear growth or linear decrease. Yeah. How did we interpret the slope, okay, in a linear growth pattern? We have already studied that. So let's see what you can remember. Do you remember the concept of the slope? Basically speaking, the slope is the rise over run. And if the run, that is the, this displacement, we just take to be 1 unit. So it would be the rise, per unit of run. So in other words, the number or the increase in oxygen uptake, per heartbeat or beat. In just, here is the beat per minute, Which of the following is the best interpretation of the slope? It says the predicted increase in Kyle's oxygen uptake in liters per minute for every 1 beat per minute increase in his heart rate. The increase in the heart rate is the run, remember? This is the run, while the rise, this is the run, and this is the rise. So per each heartbeat per minute that Kyle increases, he will increase this value, the rise, that is the slope. he will increase some kind of oxygen uptake in liters per minute. The best choice is option B. Okay, imagine that when they tell you if this rise over run is the slope, then if the run is just 1, then the slope is equal to the rise. That is the increasing oxygen uptake per heartbeat per minute. Okay, let's see another question regarding the same chart. Take a look. Which of the following is the best interpretation of the y-intercept of the line of best fit in the context of this problem? Remember, when we have linear growth patterns, we have here y, and here we have x, and here we have something like this. Okay, this is y equals mx plus b, where m is the slope and b is the y-intercept, this point. What does this represent actually, this value, b? Is the value that y takes when x equals 0, right? That is y of 0, this equals b. And what does it mean? It means the initial value of the dependent variable when, you know, the independent variable has its minimum value, 0. So according to that definition, okay, it would fit with option C. The predicted oxygen uptake in liters per minute at a heart rate of 0 beats per minute. That's exactly what the y-intercept of the line of best fit would mean. But of course, this is meaningless, although here, right, this is the correct choice. It doesn't mean anything here because in the case of Kyle, to have a 0 beats per minute would mean that he's already dead. So it would be totally meaningless, that value of the oxygen uptake at that moment. And okay, so be careful when you use linear patterns to interpret a set of data, establish some correlation between two different sets of values. Be careful not to extrapolate the given data. Notice that this data is meaningful only for a range of beats per minute that is between 90 and 130. It's totally meaningless out of that range, okay? Well then, let's see some more examples. Now, let's see this example 4. This has to do also with the concept of taking a sample of a huge population in order to make predictions. Okay, let's see. The question says, Malden is a town in the state of Massachusetts. A real estate agent randomly surveyed 50 apartments for sale in Malden and found that the average price of each apartment was $150,000. Another real estate agent intends to replicate the survey and will attempt to get a smaller margin of error. Which of the following samples will most likely result in a smaller margin of error for the mean price of an apartment in Malden, Massachusetts? So let's see each of the statements one at a time. 30 randomly selected apartments in Malden. It is true that by taking a new survey in Malden, the same place where the first, survey was done, makes sense. But could we say really that we would get a more accurate value for the average price of an apartment with a smaller margin of error just by sampling 30 apartments? If in the first study, they sample 50 apartments, which of course is not the total number of apartments. There must be a huge number of apartments in a whole town. But okay, we cannot ask the price of all the apartments. That would be impossible, an incredibly difficult task. So the person, this real estate agent referred at the beginning, he just, surveyed or sampled the prices of 50 apartments. Would we get a smaller margin of error that is a more accurate value for the price by sampling fewer or more apartments? Actually, the bigger the size of the apartments, the size of the sample will get a more accurate value. So this makes no sense. Obviously, this doesn't either, and it refers to sampling apartments in all of Massachusetts, but this is wrong because we're trying to estimate the mean price of an apartment in a specific city, not in the whole state of Massachusetts. That's why we can also cross out option D. We would need to make a new sample or survey of the prices of apartments in Malden only, but of course, with a bigger sample. With a bigger sample, 80 is greater than 50, we can actually get a more accurate prediction for the apartment's price. Okay, let's see some other examples. Take a look at this. Okay, I leave this up to you to read and study the question and see, let's discuss then what conclusions we can get about. So what's the best answer here? Actually, option D. Although you might think that perhaps the fact that monitoring the students that exercised at least once a week, they had better performance in their studies than the students who didn't exercise at all. You might think that this is the same as, causality. But the fact that the students who exercised got better academic performance, okay, that is not a proof in itself that actually because of exercising, you improve your exam scores. That there is a positive association, that is when the students do more exercises, they get, higher exam scores. That is true. But we cannot say that one thing is a cause for the other or vice versa. The causality is not so easy to demonstrate, okay? So here to say that it's likely to improve, we don't know really why people who, exercised more actually got better scores. Perhaps it didn't have anything to do with exercising at all, but some other factors, perhaps some motivation from their parents says, if you do exercise, I will buy you a new iPhone. Okay, then he will start doing exercise because in order to get the iPhone. And, the motivation to get the iPhone could make him study more or something. But we cannot prove causality. In the best case, we can talk about a positive association only, but not causality, okay? And so it's the same with the other three. They somehow involve causality. Exercising 3 times a week improve exam scores. We don't know if it actually improves. Any student who starts exercising will improve. We don't know this. It cannot be proven, actually. Okay, let's see one more example. Take a look at this. These questions may be a little tricky. You might believe that because you have some prediction of the mean pH of the water samples based on a 95% confidence interval, you can make predictions for periods other than the sample period. What does this prediction correspond to? Which period? It says here that this was, measured in the past year. Obviously, when we talk about the water that falls, that is rainfall, to find the pH of all the rainfalls in the past year, actually there are many more than just 40 rainfalls, especially in a rainy country, such as in the Northern Hemisphere. More than 40 times a year it rains. So remember that the rainfall doesn't fall just one day. In a single day, there can be many rainfalls. So the thing is, we took samples from 40 rainfalls in the past year, and this give us a measure for the pH that is in this range, in this interval. 95% confidence means that if we took, this sample measurement, 95% of the times, we would get values of the pH that would be in this range. And perhaps 5% of the time, we wouldn't. But that only is another way to say that these measures are kind of trustworthy. We can trust these measures sampled, although not for all the rainfalls that actually took place, but for the sample of rainfalls, we can trust that the real pH of the rainfall in all the past year had actually this pH level. That's all it means. It doesn't mean that we can actually extrapolate this value for a period larger than the past year. So it would be a mistake to say that it is plausible that the true mean pH of all forest rainfalls in the past decade is between 3.2 and 3.8. No, this is applicable only for the sampling period. Okay, we cannot extrapolate for other periods out of this. That is to say that the true mean pH of all the forest rainfalls in the past year is between the given range. That's the meaning of 95% confidence interval. And in SAT questions, they usually mention 95% confidence interval or 98% confidence or 99%. Okay, that would be a little more reliable, but actually 95 is reliable enough. So just means that it is plausible that we can trust these measurements. Okay, so C is the correct answer choice. Be careful, past decade is too far, for an extrapolation. Okay, let's continue. And now let's talk about the last of the math topics for the SAT. There are questions in the SAT that have to do with geometry, of course, but especially with volume calculations. In the SAT, you need to deal with volumes for several different geometric shapes in 3D. Okay, the most basic ones are the cube. For most of these rectangular shapes or rectangular solids, the basic principle for estimating the volume is to calculate the area of the base and multiply by the height of the solid. For example, in a cube, the area of the base is just one of the equal square faces of the cube. That's the base. And the height is just, the common edge. So if the edge is S, so the area of the base is S squared times S, that would yield the cube of S, obviously. If it is a rectangular box or prism, then if you have this rectangular box, what is the area of the base? Is a rectangle. And this rectangle has as area L times W. This area multiplied by the height yields the volume of a rectangular box. In other words, the volume of a prism or a rectangular box is always the product of the three edges, right? Length, weight, or width, and height. What happens with a cylinder? We can see a cylinder pretty much as if it were a prism, but with a circular base instead. So consider this is the base of a rectangular, a right cylinder. A right cylinder has a base that is a circle. So multiply this circle by the height of the cylinder and you get this formula for the volume of a cylinder. The good news is all these formulas are given at the beginning of the math section, but that doesn't mean that you don't need to be familiar with these formulas in advance. If possible, you need to remember them by heart, okay? know the formulas, you know, for each case, so that you don't need to be going back and forth, you know, the formulary or the set of formulas at the beginning. So what other formulas do you need to be aware of? Take a look. Other key volume formulas in the SAT are the formula for the sphere. Okay, a sphere is like a ball, and a ball's main measurement is the radius, right? The distance from any point in the surface of the sphere to the point at the center of the sphere. That would be the radius. Pretty much as in a circle, you know, you have the radius is the distance between any point in the border to the center of the circle. So same idea. But of course, this is in 3D, right? So here's the volumes formula, 4/3 of pi times the cube of the radius. Then for cones, you know, the cone is this construction. It's, you know, like it has a circular base, but it has a tip here, and this is a curvy surface, right? So everybody knows a cone because everybody knows, you know, the little clown cones or sometimes the Frio Rico ice cream, right? Yeah. The package for the Frio Rico ice cream is a cone, an inverted cone. So what is the formula to take the volume of a cone is 1/3 of pi multiplied by the square of the radius. So remember this, pi times the square of the radius is the area of the base of the cone, okay? This is the area of the base. And h is the height of the cone. That is a perpendicular segment from the tip of the cone to the base. So this product multiplied by 1/3, that is the volume of the cone. And what about the volume of a pyramid? If it is, for example, a quadrangular pyramid, that means that it has a rectangular base. And so you obtain the volume pretty much like multiplying the area of the base by the height, but then multiply that volume by 1/3. So it's 1/3 of the volume of a prism or a rectangular box, and similar in shape to the volume of a cone. So these are the formulas that you need to handle. Let's see a couple of examples for volume questions in the SAT. Let's take a look. For example, here, in the figure above, a cylindrical block of wood is sliced into two pieces as shown by the dashed curve. What is the volume of the top piece in cubic centimeters? So here it's interesting. What would we do in order to determine this? Think about it. If you visualize this cylinder of wood, you know, from upwards, you would see this, right? If I place the cylinder of wood and I take an aerial view, I see it from this position. Then what I will see is that this dashed curve actually looks like this division in the cylinder. So if I want to take the volume of this part, that simply is half of the volume of the whole cylinder. So it's easy. You just need to calculate the volume of the cylinder and divide it by 2. Okay? So how would we do it? Okay, you need to remember the formula. Yeah, the volume of a cylinder is pi times the square of the radius of the base times the height. This is it. Okay, see if you can solve this one. Let's see how to do this one. Okay, we've already set what's the logic. Let's calculate the volume of the cylinder 2 divided by 2. Okay, what's the radius of the base? Since the base has a diameter of 4 centimeters, that is to say that the radius is half of the diameter, 2. So we have pi times 2 squared and the height is just 5. So we get 20 pi, 4 times 5, 20. And of course, the correct answer would be 10 pi, half of the volume. Let's see another one. Okay, let's see how to do this one. First of all, if we want to calculate the volume of a cube whose common edge measures x, then we know that the volume will be x up to 3, the cube of x. And what is the surface area of a cube? Well, consider that a cube has, a surface area that is conformed by six square faces. So the sum of the areas of 6 square faces is the surface area of the cube. So the surface of the cube is 6 times the area of this common face. In other words, this. So if this is the surface area in terms of the common edge, we can equate this with this expression in order to obtain the value of x in terms of A. So let's see. We can simplify and we get here 4. So x squared equals 4a squared. We're working with only positive values. We're talking about linear dimensions. So forget about negative values here. Just x is the square root of this, the positive square root. So it's 2a. And that's it. Okay, so since this would be the value of x in terms of a, all we need to do now is substitute here in order to obtain the volume. 2a cubed would be 8a cubed. That is option C. All right, so let's now, if there's no further questions, see another sample question. Oh, Luciana, so please.
Teacher, I have a question. The formula for the surface area is 6x squared or just 6x?
No, 6x squared. Because
Okay.
when you develop the surface of a cube is like this, right? Like this figure.
Yes.
Where each of these is one face of the cube. And the edge and the side of each of these squares is x. So you have 6 squares with the same area. So x squared is the size of a single area, of a single face.
Okay. Thank you, teacher.
Okay, you're welcome. Let's continue with the next question. Take a look at this. A container in the shape of a right circular cylinder shown above is just large enough to fit exactly 3 tennis balls each with a radius of 2 inches. If the container were emptied out and filled to the top with water, what would be the volume of water in cubic inches held by the container? If the container were emptied out and filled to the top with water. So we need to understand this question. Okay, what are they telling us? Basically, what would be the volume of all the water contained in an empty recipient with a form of a cylinder? What would be the volume? In other words, what is the volume of this cylinder? That's the answer to the question. Okay? So because here, some people think, oh, what if I, like the container is now, I add water? Are they asking me about the extra water that could fit on top or on sides around the 3 balls? No, no, no. Here it says clearly, the container were emptied out. So no balls inside, just water, water to the top. All of this just water. So what would be, it's exactly as calculating the volume of the cylinder. But for calculating the volume of the cylinder, you need, of course, the formula pi times r squared times h. From the data of this problem, you need to determine the radius and you need to determine the height of the cylinder. Okay, you can try. Okay, this one is not so hard because the key is understanding words and terms in the statement very precisely. Here it says that a container is just large enough to fit exactly 3 tennis balls. What does it mean to fit exactly 3 tennis balls? That the diameters of these 3 tennis balls put in a row fit exactly within the height of the container. In other words, if you want to know the height of the cylinder, you need to add 3 diameters of the balls. Since each ball has a radius of 2, the diameter is 4 for each. So 4, 4, and 4, this yields a height of 12. The radius, of course, is the same. The width of the ball is a radius of 2. So this is exactly a projection of this radius on the base of the cylinder gives a radius of 2. So we have volume pi times 2 squared times 12. That is 48 pi. Okay, let's see another example. Take a look at this. Okay, let's first represent, graphically what is going on. We have an aquarium, it's described as a rectangular box with its 3 dimensions, right? Here it has 80 inches, here 25 inches, and the height is 30 inches. But this actually aquarium contains water to a depth of 20 inches. So here there is, some water. This is 20 inches, the height of the water. And of course, it should be something like this, right? If we try and visualize this aquarium with water. So a solid block with a volume of 5,000 cubic inches is submerged in the aquarium, and how many inches does the water level rise? It only makes sense that if we submerged, one block that is solid in this water, and here the key word is submerged. What does submerge means? That the actual, level of water in the aquarium actually covers completely the submerged object. So imagine that this submerged object is something like this, okay? It's a block. This block measures this volume. So we could only think that the actual volume that now is occupied by the block will displace water upwards. So because of this, the new level of water in the aquarium will be something like this. Because now it will ascend a number of inches, x, which is exactly forming like a layer of water above the original level of water in the aquarium. But this kind of layer of water on top of the original volume, this layer of water will have to be equivalent in volume to the volume of the submerged block. Because, any object that is submerged in water displaces exactly the same volume that it occupies inside water. So it makes water raise But here, the thing is that the volume of this layer, which is also, we can visualize this as another prism or a rectangular box whose dimensions are 80 inches length, 25 inches width, but the height is just X inches. And the volume of this block is exactly 5,000 cube inches. So this is it. We can calculate it by simply multiplying X by times 80 times 25 equals 5,000, because that's how we obtain the volume of a box, multiplying the three edges. So multiplying this, okay, you can see here that this one is 2,000, right? So, and you get X times this equals 5,000. So 2X equals 5 and X equals 5 over 2. So 2.5 inches is the rise in the water level. Okay, let's see if we have one more. Okay, that's all. And as I said at the beginning of the session, that's the end of our course theory.